Hello, travelers, and welcome to Adventures in Security. Managing information resource security is managing the associated risk, but we can't manage risk unless we know how to measure it effectively. That is the purpose of risk assessments. In this video, I look at the risk factors we use in a formal process to understand the risk associated with an organization, a process, or a system. I then show how those factors are used in an example risk assessment, both with a risk matrix and a risk calculator. A calculator that's based on an Excel-based workbook that's available for download in the video description. The script for this video, formatted as a study guide, including a selected bibliography, is also available for download at a link in the video description. Risk can be positive or negative. A positive risk is an unexpected event that actually benefits an organization's bottom line. Negative or adverse risk is the opposite. It represents a cost to the business because of an unwanted event. The NIST defines negative cybersecurity risk as related to the loss of confidentiality, integrity, or availability of information, data, or control of systems, and reflects the potential adverse impacts to organizational operations, that is, mission, functions, image, or reputation, and assets, individuals, other organizations, and the nation. In security, we typically focus on adverse risk, the type of risk addressed in this video. Risk management is the overall set of processes built to adhere to a risk management policy that, according to Technopedia, is the process of identifying, assessing, and prioritizing risks to an organization's capital and earnings, and taking steps to minimize, monitor, and control the impact of those risks. This graphic shows the elements of the NIST Risk Management Framework, or RMF, as defined by the Computer Security Resource Center. I'll touch on all of these, but we focus on assess, with links provided to other resources that go into more detail on the others. This graphic largely represents how we manage the risk associated with a new or modified system, but it also applies to existing systems that require regular risk assessments at a frequency dependent upon the system categorization and the data's classification. Step 1. Categorize a system or process, as described in the video above, to set the value of a system to the business, including assessing the impact on the business if the confidentiality, integrity, or availability of the assessed system or process is compromised. Step 2. Select security controls considered best practices based on the categorization of the assessment target. Recommended controls are found in NIST SP 800-53 Rev 5, Security and Privacy Controls for Information Systems and Organizations, the link to which is in the video description. Step 3. Implementing selected controls, ensuring the configurations needed to protect the target given the identified probable threats. This is often done after an assessment, so the steps in the order presented here might change, depending on the information the organization already has about the risk. Personally, I would conduct an assessment before selecting or changing any controls. Step 4. Conduct a risk assessment, a process that we cover later. Step 5. Authorizing the system is not something private businesses do outside a change management process. Authorization usually happens when the data owner is satisfied with the residual risk, a risk left after the implementation of reasonable and appropriate controls. And finally, Step 6. We monitor the system's behavior or the process's outcomes to ensure we are achieving the security outcomes that we expect. Organizations should conduct process and system assessments at a frequency that reflects the resources categorizations and classifications. This means that the framework cycle is continuous, with steps performed as needed. At a high level, we perform assessments to identify, prioritize, and manage risk, but we use risk information for multiple purposes. According to NIST SP 800-30R1, risk assessments are needed so we can develop an information security infrastructure, define system interconnection requirements, design security solutions for systems and the environments in which they operate, design processes that safely provide needed business outcomes, provide the risk information needed for system authorization, prioritize and manage risk, reducing residual risks to levels acceptable to management, and finally, effectively manage security solutions like monitoring, behavior analysis, and ongoing vulnerability management. Risk is the result of multiple factors. This is often depicted with the simple formulaic risk model, risk equals threats times vulnerabilities times business impact. However, the assessment of risk is far deeper than this, as shown in this graphic. Let's look at each of the factors shown. A threat is any event that can adversely affect an organization's bottom line and is divided into two elements, a threat source and a threat event. A threat source is a human or non-human entity, also known as a threat actor or TA, that exploits vulnerabilities in a system or process attack surface. In this video, I focus on human TAs. All TAs are not the same. They have different motives and skills, including financial gain, terrorism, activism, or just as a challenge. Motive determines how much time and effort a TA is willing to spend on an attack. Another characteristic of a threat is means, tactics, techniques, and procedures, or TTP, the skills possessed by the TA. Means also changes according to the threat. For example, a nation-state or organized crime actor will likely have the training, tools, and financial backing to maintain attacks against even the best defended resources. As we prepare to complete an assessment, one of the first steps is the identification of probable threats and the amount of effort they would be willing to spend, how skilled they have to be, and their probable motivation. These factors affect the likelihood of occurrence, the probability that a TA will successfully exploit one or more vulnerabilities along an attack path. They also affect the kinds of safeguards needed. A threat event, commonly known as a security incident, occurs when a TA exploits one or more vulnerabilities to partially or completely achieve attack objectives. As you can see, a vulnerability does not exist in isolation. It's surrounded by safeguards, including access controls, intrusion prevention, and continuous monitoring. The existence of safeguards and the resource targeted determines the severity of a vulnerability. Not all vulnerabilities have the same severity, even if labeled critical by a vendor or other source. The use of tools like the CVSS calculator help us identify the actual severity of a specific vulnerability within our own operating environment. The link to my video on how this works is in the video description. As I mentioned earlier, a threat's means and motives contribute to the likelihood of occurrence. In addition, the predisposing conditions of each vulnerability required for an attack, measured against the required TA-TTP and overall effort, complete our understanding of the probability of a successful security incident. The financial impact caused by an incident can be short and long-term, including loss of sales, shareholder confidence, customer trust, regulatory penalties, and litigation. Costs directly related to incidents include resource replacement and third-party recovery assistance. The impact is largely based on the value of the target, including development or acquisition costs, administration or management costs, costs of maintenance agreements, total safeguard costs, a value that requires that you understand all associated administrative, technical, and physical controls, information that is often completed during threat modeling. Value to competitors, a value that might cause them to cross the line and steal or damage your assets. A common threat for intellectual property that provides a significant competitive advantage or enhanced national defense. Replacement costs, production costs for loss of supported business processes, consisting of the loss of revenue, competitive advantage, or an edge in national defense, including impact on upstream and downstream systems and business processes. Operational costs, and liabilities of asset loss of confidentiality, integrity, or availability, including regulatory fines or customer litigation. We use this information to categorize our target system and to classify the data it processes or stores. For a detailed look at asset categorization and classification, watch my video at the link in the video description. We arrive at the level of risk in one of three ways: quantitative or semi-quantitative calculation, or qualitative analysis. Quantitative calculation involves the use of actual dollar amounts using a four-step process. First, calculate the value of the target resource. Second, calculate the expected loss related to a single incident, the single loss expectancy, or SLE. SLE is affected by the presence of a documented and a practiced incident response plan. A quick and effective response limits loss associated with an incident. 3. Calculate the annualized rate of occurrence, or ARO. For example, if the team believes that an identified incident has a 20% chance of occurring each year, the ARO is 0.2 or 0.20. The ARO is related to the likelihood of occurrence. And finally, multiply the SLE by the ARO to arrive at the annual loss expectancy of ALE. For example, if the SLE of an incident is $100,000 and the ARO is 0.20, the ALE, or annualized loss expectancy, is $2,000. In other words, the SLE is the annual cost of a single incident when total cost is spread over 5 years, the expected repetition cycle of the incident. Qualitative assessments use tools like risk matrices and the knowledge and experience of the assessors to determine a level of risk, a level measured by a numeric range. I demonstrate how this works as we step through an example. Semi-quantitative calculation uses a more detailed numeric analysis to arrive at a risk score that has an accuracy that lies between full quantitative and qualitative approaches. It's important to understand before we proceed that qualitative assessments include some discussion of estimated costs. As we work with managers and with data and system owners, the discussion and qualitative ratings often hinge on those estimated costs. So let's step through a simple qualitative analysis. The first step in any assessment is defining its scope. This is part of framing the process. Framing includes selecting the assessment method, in this case qualitative, and establishing the boundaries within which the assessment is performed. This graphic shows a set of systems. The target of our assessment is the accounts receivable system, a system that includes payment card information. To clarify, a system is the set of technology that enables one or more business processes, including subjects, which are the user. A subject is the user application, and the device used by the user. Switches, hubs, routers, servers, storage, cable runs, and network jacks. In this example, we first identify the elements of the AR system, those we intend to include in our risk assessment. The assessment team decides to include the AR clerk, the AR clerk desktop computer, the workgroup switch for AR, the layer 3 switch, the financial database servers, the AR applications, and the AR application server. Once we understand scope, we can approach assessing risk by identifying threats to the assessed resources and then stepping through their probable paths, identifying vulnerabilities, and then assessing associated threats and the likelihood of vulnerability exploitation. In other words, we're going to identify the attack surface of our system. In this video, the team uses the first approach, which also results in vulnerability assessments. That's the approach where we identify threats to the assessed resources first. The second approach is often used when a new vulnerability is announced, as described in my CVSS video in the video description. The specific threat type assessed in my example involves a compromise of a subject and a threat pivot to attempt access to other systems. To achieve this, a TA can follow one or more paths to reach his objective. Consequently, the first step in the process is stepping through each attack path, assessing the associated controls and vulnerabilities, and the likelihood that a TA can pass through each step along the path to achieve those objectives. One of the best tools for doing this is an attack tree, a tool used for what we call threat modeling. Threat modeling helps us understand the strength of our defense along each attack path. I take a deep look at this in my threat modeling video at the link in the video description. The threat for our example is the delivery and installation of an attack package on the AR Clerk device, enabling pivoting to attack other resources. We'll ignore fileless malware for the purpose of this walkthrough. The first step is to build the attack tree. We start at the resource and move down toward the TA. The team creates this tree to model this threat. Note that only one complete path is identified and stubs for the other tree limbs and nodes are provided. There are many approaches to constructing an attack tree. I use Boolean and OR gates to indicate that either one or more of the actions in the yellow circles must be successful, or that all previous actions must be successful, the AND gate, for the threat to proceed. Further, there is no one way to display this attack using a tree. Each team will use an approach useful for the assessment intent and compliant with an accepted model. After building the tree, the team steps up from the bottom, assessing each action a threat actor might or must perform successfully, and assessing how well existing controls decrease the likelihood of threat actor access at each action node. The team also identifies and notes the vulnerabilities found. Starting at the bottom left, we assess the ability of a threat actor to gather information via open source intelligence or OSINT, information that can provide the TA with opportunities for subject compromise, including subjects in business roles that provide the best path to collecting payment card information, or PCI. The team uses tools like those described in the video above to determine that there is sufficient information about the organization across multiple internet sources for the TA's purposes, so they rate the probability of the TA's success at this node as very likely. This ranking is based on their selected risk matrix, as shown here. They then assess the possibility of passive reconnaissance success. The team discovered that the current next-gen firewall blocks any external traffic that is not associated with a session initiated within the organization's network, has a source IP address included in blocks of geographic or known malicious IP addresses, and the IPS in the firewall and the firewall itself are up to date and hardened according to vendor and security best practices. The team rated the probability of using this node in an attack as unlikely. Note that even though the right controls are in place, there is still a residual probability of compromise. At this point, because of the OR gate, the probability of attack remains very likely. The next level in the tree includes two nodes that are both required for TA success. This is due to each of the nodes enabling one of three nodes in the next level required for attack success. This is indicated by the AND gate. The first node examined is the TA's ability to create an attack package. Because the TA can gather sufficient OSINT for target identification, including technologies used on the target desktop, she is able to create an attack package. The TA can use this information to target specific users, like our AR clerk, with malicious links on websites, social media, or email messages. So far, we have a very high probability of a successful attack. Now we arrive at a level in the tree where the team has the most control. First, the AR clerk has to fall for the lure. The team determines that a strong training and awareness program, starting with new hires, greatly reduces the probability that this will happen. An additional control, email filtering, helps keep suspect messages from reaching the users. Web filtering, configured in the firewall, helps keep the users away from high-risk and known malicious websites, including social networks. The ranking for this node they make unlikely. The next node involves the successful delivery of the attack package. Because existing controls strip all high-risk attachments from external messages, the TA is unable to deliver attack packages in this way. These controls make it difficult, but not impossible, to achieve this node objective. The ranking for this node is possible. The final node at this level requires the installation of the attack package. Group policy prevents the execution of macros not explicitly approved by security, and users are not allowed to install any applications not included in the approved application list. However, this doesn't stop the installation of fileless malware, and the organization does not monitor user and entity behavior. The team decided to rank this node as possible. The rankings so far result in an unlikely probability of attack success. The probability depends on the lowest node rankings, with unlikely at these critical points. Consequently, the overall probability is unlikely that a TA can gain authenticated access to the AR application, but there are two additional subtrees that need assessment. The most effective approach is to perform analysis on all branches, and then design controls that minimize the likelihood of occurrence across multiple nodes. Yes, this is a very simple assessment, one that would likely contain more nodes after team brainstorming that usually produces a significant number of probable threats and associated tree nodes. After determining the probability of occurrence, the team decided to use a risk matrix to determine overall qualitative risk. This risk matrix is just one example. There are various ways to build a matrix, including adjusting the red, yellow, and green areas based on management's risk appetite overall or for the system assessed. It's important to define what each of the columns and rows represents clearly. Again, how they are defined is dependent on the organization and its unique operating environment. These tables show how I defined them. We plot these values on our matrix, falling on a yellow square. The square colors represent green, acceptable risk, yellow, moderate risk, and red, high risk. How the organization manages these levels depends on the controlling policy and management's risk appetite. Management is usually reluctant to spend the time to determine all the actual costs associated with an incident, and qualitative assessments often don't go far enough. Semi-quantitative assessments look at more risk factors, providing a reasonable and appropriate risk score. For this example, I use a tool I created several years ago. You can download this tool from the link in the video description. The first two columns represent a threat vulnerability pair discovered during the assessment. Remember that a single threat actor will likely have to exploit multiple vulnerabilities along an attack path. Consequently, the tool usually consists of sets consisting of a single threat actor and multiple related vulnerabilities. Likelihood is divided into means and motive, the capabilities and intent of the threat actor. The means and motive tabs at the bottom of the workbook provide guides for the scores. Business impact is calculated using the system sensitivity, vulnerability severity, and controls and response. During preparation, we have to determine the value of an asset. Asset value is made up of various values, as shown in the system sensitivity calculator. The total value is added automatically to the system sensitivity column. The vulnerability severity values are under the vulnerability security worksheet, and the anticipated effectiveness of the existing controls is scored using the controls worksheet. Tolerance is a percentage representing management's risk tolerance. 100% is zero tolerance, with 0 representing no management interest in the risk. This value can also be used to weight risk values. For example, if an assessed threat vulnerability pair only applies to confidentiality, but it is the integrity of financial data covered by SOX, that is affected, tolerance might be 75%, lowering the overall impact for prioritization. Prioritization that would move integrity issues that have a 100% tolerance value higher on the risk management action plan list. The risk is calculated with means plus motive times system sensitivity times vulnerability severity times controls times tolerance. The risk score for each threat vulnerability pair is assessed based on the table in the risk worksheet. Remember that all tables in this tool should be adjusted for your business and possibly for each system. The best way to learn how this tool fits and how it compares to the CVSS calculator, see video description, you need to work with them. Not every tool or approach works best across all industries and business models. Once an organization determines the risk levels, each risk is managed in one of 4 ways. It is mitigated, transferred, avoided, or accepted. We mitigate risk with controls, also called safeguards. When considering one or more controls needed to reduce risk, the annual cost of the control should not exceed the potential annual risk, also known as the ALE, in quantitative analysis. When using quantitative or semi-quantitative analysis, security must work with management to estimate the difference between controls cost and potential risks. When the cost of mitigation is too high, the security team might recommend risk transfer. Transferring risk is the transference of a portion of the risk costs to a cyber insurance company. It's important to understand that purchasing cyber insurance does not relieve the organization of overall responsibility for protecting the assets for incidents that will eventually happen. Costs that cyber insurance might not cover include loss of shareholder confidence, lack of customer confidence, and loss of long-term revenue. If the potential cost of an incident does not exceed the value of what is causing the risk, or if the cost of mitigation or transference is too high, management can either accept or avoid the risk. Avoiding risk, the removal of the process or technology that's causing the risk, is an uncommon approach. This is usually because the cause of the risk is a process or supporting technology needed for existing or improved business operations. I gave my team a prime directive for working with project teams: get to yes. Getting to yes means working with the project team to achieve the business benefits expected by the completion of the project in a way that minimizes risk. There is always more than one way to implement risk-causing processes and tech, ways that result in acceptable risk. We just have to find them. Risk management has many working parts that need adjustment based on the system assessed and the related operating environment. The information in this video is only intended as a guide that describes how I adjusted the NIST resources to meet my security requirements for a national healthcare company. That's it for this video. If you have questions, please ask. And if this information was helpful, please subscribe. And until next time, be careful what you click.